Hi everyone, and welcome to the next presentation on electromagnetism. In this presentation, we'll be introducing magnetic fields and how to draw them. We'll be looking at calculating the amount of magnetic field produced by a current, and then we'll be finishing off with just a brief chat about magnetic flux density. So if I said the word magnet to you, you would immediately think of sort of the magnet that sticks to your fridge, or this sort of magnet that you would have played around with when you were younger. And then you've also got these horseshoe magnets, which you don't see as often anymore. But a magnet, in terms of the colloquial sense, is a material that generates its own magnetic field. So iron can do this, nickel can do this, and cobalt can do this. And we'll talk about the difference between hard and soft iron later on. So a couple of basic ideas when we are describing magnets. Magnets have a south pole and a north pole, and just the same with the electric fields. The opposites will attract and the same poles will repel. So if you put a north pole next to a north pole, it will push that north pole away. But if you put that north pole next to the south pole of a magnet, then it will attract it, and that's what you see when you see magnets stick together. Now, we can draw field lines to demonstrate magnetic fields, and it actually helps us highlight whether there is repulsion or attraction taking place. And the convention is that magnetic field lines run from north to south. So the arrows will go from the north pole to the south pole. So as an example, have a crack at this one yourself. Could you draw for me the field lines between these two bar magnets? So I think it's important you first start by showing that the north is going to the south, and then how this transpires for the rest of the magnet sort of might look like that. And then don't forget that this north will sort of create a field to itself, which means the same thing's happening over here. And then immediately what you notice is that all the lines from north are going to south universally. So if you look around the north poles, you will see that you're creating all the norths have exits and all the souths have light arrows going into them. What you're demonstrating there is the attraction between the north and the south. What I'll do now is we'll have a look at when you have those poles next to each other. Okay, now what if we have magnets that have the north poles close to each other? So we know that in this situation, the magnets will repel one another. But let's draw the field lines, knowing that we need to go from north to south, and that, of course, the field lines can't cross one another. So we start by saying, okay, well, this north is going to go there, and we'll do the same thing on this side. That's fine. That's making plenty of sense. But as we start to come out from north more often, we notice that we don't want to run into the other north. Oops, terrible drawing on the fly here. Now what you're probably noticing is that the field lines are starting to become a little bit more compressed around this region here. Now, this sort of compression of the lines tells us that the field is sort of intense, and you can see that the lines are pushing one another away, which shows us that those magnets will repel one another. Okay, so in this first lab, what I'm going to do is I've got two bar magnets here. They stick together like so no worries, attraction. Remember, if I flip it around and I've got two like poles, they will start to repel each other. Okay, so now what I'm going to do is I'm going to remove this piece of paper. I'm going to put the two magnets so that they attract one another. So I have the opposite poles next to each other. I'm going to put this piece of paper over the top, and then I'm going to use iron filings. Now, what the iron filings will do is actually help draw the magnetic field. Now, if I put enough of this down, and then I put some more in there, what you can see is that the field lines are starting to line up. So notice that you can see that the field line is going straight from one side to the other. Okay, so now I've got the magnets so that they will repel each other next to each other. So I have two like poles facing each other. And if I put this over the top again and then get some iron filings, put some more. What you immediately notice is that field in the middle there is no longer connecting between the two poles. what you see is that they're diverging outwards, which is what we saw in those diagrams. And there you have it. And one more thing before we continue is looking at the magnetic field of the Earth. So when we hold a compass in our hands, it typically points north for us, and that's what we think it does. But what it does is it follows the magnetic field lines. So since the field lines go from north to south, a compass actually points to a south magnetic pole. So it's important that when you're looking at questions that talk about the Earth's magnetic field, understand that the south geographic pole is where the north is, and then the field lines go from there to the geographic north pole, which is, if the Earth was a bar magnet, would be a south magnetic pole. Okay, so that's a bit of a recap on the basics of magnetism. What we're going to be getting into now is looking at how charges are actually responsible for producing the magnetic fields. And I'm not just talking about charges running through conductors, but I'm also talking about charges within substances, including orbiting electrons within a substance like a permanent magnet. It's important that if you don't understand something as we go through this, please seek clarification, because it's very easy to get this back to front. And when you get it back to front, it's very easy to lose lots of marks. So we'll start off with looking at iron. So iron is a really common magnetic material, and we can sort of put iron in two different categories. If we can say that it's hard iron or that it's soft iron. We say that the substance is made up of these domains, these sort of magnetic domains that align in certain directions dependent on the field. So hard iron, those domains will align a certain way and create a magnetic field, and it's very hard to sort of change that. Soft iron, however, might look a little bit random, like the diagram over here on the right, and then when it's under when a magnetic field is exposed to it, then it will actually align with that magnetic field and help almost amplify that field. Okay, and this brings us to one of the first concepts that we're going to be learning in this course, and that is the magnetic field around a current. So what we've observed, and we'll be showing this in experiments, is that when you have a current passing through a wire, remembering that a current is the flow of positive charge, when you have that current flowing through the wire, it generates a magnetic field, and the magnetic field surrounds it in sort of circles radially, and the direction of that field we can determine using the right-hand rule. We'll look at how we can quantify how much field there is later on, but first, let's just get the direction sorted. So if you get your right hand and just do a thumbs up, like a little Fonzie, like this one here, if your thumb represented the flow of positive charge or the flow of current, then the fingers and the direction that they wrap around your wrist or wrap around your hand, that would demonstrate the direction of the magnetic field. So which direction that field goes. So if we were to sort of place a compass here, that compass would therefore point in this direction. It will point in the direction of that field line. And if we were to sort of make the current going in the opposite direction, then as you'd expect, the magnetic field lines will reverse. And we'll do plenty of examples of this later on. Okay, so what I've got in front here is a bar magnet with these little compasses next to it. So you notice that the compass in this case is pointing outwards. So this is what you expect it to be going out, which is fantastic. So this would be our north pole, and as you can see, it goes in there to the south pole. So you can see the arrow, and if you can spot it, but it's mostly in. And then what you see is as we go around, the field is actually doing what we expect it to do. So that one there is coming in. So you can see the field's come around and now it's coming back in and so on. Now, if I get one of these magnets and move it around, what you'll see is that it'll continue to point to that south pole, or it'll follow the line. So you see it changes until it comes out far enough. And then when we get there, you can see that it's now facing the south pole, which is pretty cool. Now, where it gets even more interesting is I've got this wire, so I'm looking at the red wire here, and what I'm going to do is I'm going to turn on the power pack, which is going to induce a current. So here's my positive, and my positive is going to be going up that way. So the current will be traveling upwards. So if I use my right hand rule, thumb going upwards, which means the magnetic field should start to go around this way. So what we should see, if I was to put the magnet next to it, is that the magnet will follow around. So we should see it go around, always face as anti-clockwise direction. So I'm going to turn the current on. Now it might trip because I'm putting a current through it for no reason. So I've turned it on, and here we go. So as I go around, you can see that now it's flipped direction as it's going this way. There we go. And now it stops, so now it's just going to face any way it wants. So when you hear that click again, it'll activate, and hopefully we'll see it go in the right direction. There we go. Around we go. So we know that the direction of the field can be shown with the right-hand rule. Before we start looking at applying the right-hand rule, it's important that you know how to draw and demonstrate your knowledge of electric and magnetic fields. So these are just some pointers on when you're drawing magnetic or electric fields using two-dimensional diagrams. So the first two are fairly straightforward. When you want to draw a field going to the right, you just draw a line that sort of goes to the right. And when you want to draw a magnetic field or an electric field going to the left, you just draw it going to the left. So as an example, I'm going to say these are magnetic fields, and magnetic fields we give as a B. So I'm just going to put a B there, and I'll put a B there. Now, where we go into sort of new territory is if you wanted to demonstrate to me that the magnetic field is coming at you out of the page or going away from you into the page. So the way you look at this is if you are looking at an arrow which represents, so like a bow and arrow, that's representing that vector. If you're staring at an arrow that's sort of coming towards you, what it will look like is effectively these little dots, won't it? So think of, so when you're drawing a field that's coming out of the page, you want to draw a dot, or what you'll see a lot of the time is a dot with a circle around it. And that tells us, looking at it, that the field is therefore coming out of the page. And if you wanted to draw a field that's represented as going into the page or going in that dimension, then if you're looking at an arrow that's going away from you or into the page, what you would see is the feathers behind it. So it'll look like a cross. And sometimes you will see it where it's a circle with a cross inside it, like this one here. Okay, so that's all well and good, but we need to be able to apply those relationships. So remember that you have a right-hand rule and your thumb points in the direction of the current and your fingers wrapping around that current tell you the direction of the magnetic field. So looking at these four examples here, so we have example 1, example 2, example 3, and example 4. Think of those as the direction of current. Could you, for me, draw the magnetic field for each of those currents? And again, the magnetic field doesn't have to be a straight line because, as you know, in one of the previous slides, the magnetic field wraps around a current. So you will need to be a little bit clever with this. Give it a go. Okay, so now we're outside of the computer, we can do these problems. So with this first one, it's going into the page. So if this was your hand and you have your thumb, which represents the flow of charge or the current, it's going down into the page. So your fingers are going to be wrapping around clockwise. So you would draw your field going around clockwise. Now, I'm also demonstrating through the distance between the lines that the amount of magnetic field decreases as you get further away. For number 2, it's the other way around, so it's coming out of the page, thumb out of the page, which means the fingers are wrapping anti-clockwise. Okay, so question 3 and 4, I'm going to do them in two different ways to show you two different ways that you can represent this three-dimensional field. So the thumb is going to be going to the right, and that means the fingers are going to be curling up and over the arrow. So I can show this by putting dots here to show that it's coming out of the page on this side and going into the page on this side. Now for this one here, the current is going up, which means it's going to be going around like so, which means it's going to be going, I can draw it like this. But as you can see, when you draw it like this, it can sometimes be a little bit difficult to understand. So it's up to you. I don't really see many field lines in tests or exams that are a little bit ambiguous, which is great. But what you might find is if you have photocopied worksheets that you find online, you might find some field diagrams that are hard to understand. Okay, and this is an example experiment that we'll try to do later on. But if you have two wires, so pairs of wires sitting next to each other, so you could have like a power supply over here and then you have like one wire coming out of it like that, another wire coming out of it like that, and then you have the current, for the first one, the current's going away from the power supply. And what they'll generate is two magnetic fields, and then they can interact with each other. So what this question is asking you is what's going to be happening to the magnetic fields in each case, in each set, and will they attract or repel? Okay, so if I was to draw my field line here, I would have going into, so what I'll be drawing is the field lines doing this. And what you immediately find out is when I draw the next field line, it actually works well with the other conductor. So they combine, which is very handy. And when you do this one as well, what you should find is they will do the same thing. And because they're blended together, because they're working together, they will actually attract one another. Okay, so for this one here, what you've got is the charge going down. So the first, you'll have this sort of thing happening first, and then this one is going to be opposing that. Now the thing is, they don't work together, which means as you draw your next field lines, they can't cross one another, so they'll compress as they get closer to one another. So what you'll find is, well, I don't want to touch the lines, and you can see that there's a huge build up there, and that's going to create this repel effect. And this one is going to be exactly the same. Well, not exactly the same, opposite really, isn't it? Opposite direction. And that's going to be a repel as well. And hopefully we'll be able to get that experiment for you. All right, so the final demonstration is these long pairs of wires that we've got over here. So essentially what I've got is a pair of wires that go up and they come back down. And what that means is that on one wire, the current is going in this direction, and on the other side, it's going in the opposite direction. So if you remember from our little bit that we did earlier, this should create a repulsion force. So I've jacked up the voltage a bit, so it will only last for a little while, but if I turn this switch, what you should see is that repulsion. There you go. And that click just means that it's ran out of current again. So we'll do it one more time. There we go. And that's about it. Okay, and this one is always one that stumps students, is if we have this wire and the current is going in this direction because it's going from positive to negative, can you tell me which direction the field lines are going to be moving overall? And then tell me what is the north and the south pole in this magnet. So where is the north and south pole in the magnet? So we call this a solenoid. All right, so you start by, obviously here, as an example, here your field line is going to be, it's going to be going out, coming out and then going in, wrapping around the top of it. So you can follow that visually, and then this is a tough question, but see how you go with it. Okay, so the field line is going to be, the fields are going to be coming out and around like so, and here it doesn't really matter. But as I generate it here, what you notice is, so I'm looking at behind the core of the solenoid, the field line is coming out and then going in through the green part. And you'll notice it's going to be doing the same thing. So following it around, so here's my current following it around, and it's coming out, and you can see that my fingers are facing inside of that core. As I keep following that current around, notice that my fingers are actually still moving in this direction. So what actually happens is the field line going underneath, or the field line in the middle of the core, are always coming out. So on the inside of this core, the field lines are going in this direction. On the outside of the core, it's wrapping over the top. So outside of the core, it's actually coming back around. But on the inside of the core, it's coming through. So what this solenoid, so what this wrapped wire has created is a net magnetic field that goes through the middle of itself and then comes back around to the other side. Now, if you think back to your magnets, that would mean that this would be a north pole and this would be a south pole. And we can test that one too. Okay, so we're back inside the computer and we're going to... Okay, so we're back inside the computer, and what I want to do now is start looking at quantifying those magnetic fields. So we've drawn them, we've investigated them in repel and attraction. Let's look at how to figure out how much magnetic field we have. And there's two words that we use. The first of these is magnetic flux. So when you have these lines over here, think of these lines as being magnetic flux lines. So the more lines you have, the more flux you have. It's the same in this diagram over here. So here you've got the same amount of flux, because if you counted the number of arrows, it'd be the same. But the second word is looking at the magnetic flux density. And that is the amount of field, or the number of lines within a certain area. So if you have the same number of lines in a smaller area, like in this case here, then you would have a higher flux density. And over here, because you've got a larger area, you'd have a lower flux density because they're not as closely packed together. Okay, so you know that we're using magnetic flux density to sort of quantify how much magnetic field there is in a certain amount of space. So if I was to look at this current carrying conductor here, it's a dot that's coming out of the page, which means that the field is going around anti-clockwise. And notice that I've drawn the lines to be a little bit further apart from each other, which demonstrates that the amount of flux decreases. So the flux density decreases as you get further away, which makes sense. Just like a gravitational field, the further you're away from that center of mass, the less dense those flux lines become, or the less force you would feel, the less gravitational field, and same way here, the less magnetic field. So if we wanted to find out what the flux density was at a particular point, we can use this wonderful equation right here. And that is that the flux density, or the magnitude of the magnetic field, is equal to a constant, which is the permeability of free space, or it's also known as the magnetic constant, multiplied by the current in the wire, which is really important, and we divide that by 2 pi and the distance from the wire, or the range. And what this tells us is that as the current in the wire increases, so does the magnetic field. And that's exactly what you expect. If we increase the current in this particular wire, then this magnetic field, this magnifying glass would experience a greater increase in magnetic field in response to that. And as you increase the distance, you would also expect it to decrease. So as this magnifying glass came further away from the current, then yes, the magnetic field will be less, which is also something that makes sense. Now, something that makes this a little bit strange is that this is R and not R squared. So it's not an inverse square relationship like a lot of the other ones. And that's because, remember, this is not a point source. This is not just a charge. This is a current running in a wire. So rather than spherical spreading, we're looking at cylindrical spreading. So instead of being inverse square law, it's just an inverse relationship. Okay, so let's finish off with a simple problem. If we have a magnetic flux density of 1.5 times 10 to the negative 5 Tesla, and that's measured at a distance of 3 centimeters away from a long straight wire, calculate the current flowing through that wire that will create the magnetic field. So you've just got a wire, the current's going through it. In this, it doesn't really matter in direction, and it's just asking what is the current in this wire that will create a magnetic flux density that gives us a certain amount of field sort of, at this point, which is, 33 centimeters away. Okay, so this is a straight up application, right? So you have the magnetic field is equal to your mu naught I over 2 pi r, and this is where your data sheet is going to be pretty much essential. You can rearrange it right now if you like, which is what I'm going to do, and that's going to be equal to 2 pi r times the magnetic field divided by the magnetic constant. And if I put those values in, so notice I've just put the pi in rather than the value that's in the data sheet. I get 2.25 amps. And there's your answer. And hopefully you got that one too. So that's it for this presentation. The key here is just understanding some of those concepts, getting the direction of that field, and being able to get these basic calculations done as well. All right, good luck.